Have you ever looked up and felt that deep, quiet realization the universe is far stranger than we can imagine? We often focus on the stars we know, the planets orbiting our sun, but out beyond the familiar, the cosmos holds phenomena that redefine reality itself. We're talking about things that twist light, defy gravity, and emerge from the void in ways that are both scientifically rigorous and utterly mind-bending. What happens when a star dies? It's not just an explosion. It's a cosmic event that can leave behind structures so dense they become holes in the fabric of space and time. Or consider the objects that flash with incredible, predictable regularity, not stars, but the remnants of stars, spinning faster than any machine we can build. This is the place where we explore these cosmic wonders. If that calm, knowledge-driven journey into the unknown sounds like your kind of nightcap, a gentle like and subscribe really helps others discover our channel. Fall asleep with science. Settle in. Tonight, we look at the fascinating, challenging, and profoundly real phenomena to be found in the universe. The universe is an immense and incredibly complex structure. Every single one of its elements, from the smallest atomic particles to the colossal superclusters of galaxies, is strictly governed by a relatively small set of inviolable physical laws. When certain external conditions and internal specific characteristics come together, these laws give rise to truly amazing and often bizarre objects and phenomena. In this exploration, we will look closely at some of the most fascinating examples. We begin our journey by visiting the Orion Nebula. This is one of the largest and most dynamic star-forming regions, or stellar nurseries, known in our own galaxy, the Milky Way. Following this deep dive, we will turn our attention to an extremely powerful and potentially dangerous space object, the black hole closest to the Earth. Our path will then take us to a selection of unusual exoplanets, each demonstrating properties so anomalous that they are rightly considered peculiar even by cosmic standards. We will then plunge into the deep, dark emptiness of interstellar space to search for the mysterious and elusive traces of rogue planets, worlds drifting freely without the gravitational anchor of a star. Our exploration will then lead us far beyond the boundaries of the Milky Way, where we will examine a few truly bizarre galaxies. Finally, we will cast our gaze over the universe's largest scale structure, which will allow us to glimpse its most mysterious and empty regions, the supervoids. The vast majority of star formation across the galaxy takes place within these immense clouds. These stellar nurseries are known as nebulae, and they are richly scattered throughout the Milky Way. Some nebulae are comparatively modest in size, while others stretch for tens and even hundreds of light years across. These are simply vast, sprawling clouds made up of interstellar gas and dust. Over immense spans of time, the material within them is relentlessly compressed by the forces of gravity. This gravitational compression is the key engine that begins the process of stellar birth. Most of these tremendous cosmic clouds are incredibly faint and are barely visible against the dark abyss of space. They require sensitive telescopes and long exposures to be observed clearly. However, a select few are bright and large enough that they can actually be seen from the Earth with the naked eye. One of the most famous and accessible of these structures is the Orion Nebula, which scientists catalog as M42. This breathtaking structure is located approximately 1,344 light-years away from Earth. If you look at the constellation Orion, the nebula is the middle object in the so-called Sword of Orion, appearing as a slightly fuzzy point of light produced by three relatively bright sources in a visible line. Its sheer size and its comparative closeness to the Earth have made the Orion Nebula a highly attractive subject for scientists ever since the early days of telescopic astronomy. It is hardly surprising, therefore, that this great structure is one of the best studied space objects in the night sky. A major milestone in our understanding of the Orion Nebula occurred when the Hubble Orbital Space Telescope beamed back the first detailed images of the region back in 1993. These images allowed the rich diversity of its colors and complex structures to be appreciated in astonishing detail. Most of the material in these images appeared as a reddish or bluish-purple hue. The reddish color is characteristic of hydrogen gas, which is the primary component of the nebula, being excited by intense stellar light. The bluish tints often come from starlight reflecting off the dust particles within the cloud. However, the analysis also revealed unusual bright green lines emanating from some peripheral areas of the nebula. This phenomenon initially perplexed scientists for a long time. The specific radiation they observed did not seem to match the expected signature of any known chemical element at the time. This puzzle led to the proposal of a fascinating hypothesis. Early astronomers suggested there might be a hypothetical element they tentatively named nebulium, arguing that it was not present on our planet but was somehow abundantly scattered across the clouds of space. With the crucial advancements in science and physics, this mystery was finally resolved. It turned out that the green light was not emitted by a new element at all, but by extremely rarefied and ionized oxygen. When the density of oxygen gas is extremely low, the atoms are forced to release energy at specific, long-lasting wavelengths that we perceive as green. This discovery was critical, as it accounted not only for the bizarre illumination of the Orion Nebula, but also for the colors of many other nebulae observed throughout the cosmos. The Orion Nebula is not just a beautiful cloud of gas and dust. It is a factory. It is a dense, active region where new stars are continuously being born. There are currently not less than 3,000 stars discovered within the Orion Nebula to date, many of which are very young. In addition to these fully formed stars, the nebula is filled with giant clouds of interstellar gas and a great number of protostars, stars that are still in the early stages of forming from collapsing material. All this amazing diversity of space objects is concentrated in an area spanning roughly 23 light-years in diameter. All the stellar and gaseous components here are continuously and elaborately interacting with each other, exchanging energy and influencing each other's evolution. The overall mass of the material concentrated in this relatively small area is estimated to be around 10,000 solar masses, indicating the tremendous amount of stellar material packed into this region. When we look closer at the heart of the Orion Nebula, we notice several clearly defined features. The most outstanding of these is a small, bright grouping of stars known as the trapezium, which is also cataloged as Theta 1 Orionis. This grouping is an open star cluster, meaning it is a loose collection of stars born from the same original cloud. The cluster is quite young, estimated to be only about 300,000 years of age, which is incredibly young on the cosmic timeline. The trapezium is made up of 8 main components, or stellar systems, though many more fainter stars are being discovered all the time. Some of these components are binary stars, orbiting partners, while others appear to have no close companions. The brightest and most noticeable of the trapezium stars are 4 prominent stellar systems, designated by the letters of the Latin alphabet: A, B, C, and D. These 4 bright, hot stars lie very close to one another, all contained within an area only about 1.5 light-years in diameter. Each of these four principal objects has a mass between 15 to 40 solar masses. This immense mass means that these are all extremely young, extremely hot, and highly luminous stars. Massive stars burn their nuclear fuel much, much faster than smaller stars like our sun, meaning they live their lives in the fast lane and will ultimately have a short, dramatic existence. Theta 1 Orionis C is the most massive as well as the brightest star, not only within the trapezium cluster, but actually in the entire nebula itself. It is classified as a white and blue main sequence star, meaning it is currently fusing hydrogen into helium in its core, just like the Sunday. Its mass is roughly 40 solar masses, and its radius is approximately 8 times that of the Sunday. This massive star has a surface temperature of approximately 45,000 Kelvin, which makes it searingly hot. Its luminosity, or total light output, is about 250,000 times higher than that of our Sunday. The intense, high-energy radiation pouring out from Theta 1 Orionis C is so powerful that it illumines virtually all the nebula around it, acting like a giant flashlight shining into the surrounding gas. However, there is hardly any interstellar gas in the immediate vicinity of the star itself. This is because it is typical for objects of this highly massive class to experience an exceptionally powerful and relentless phenomenon called a stellar wind, which is a continuous outflow of charged particles. This stellar wind acts like a colossal broom, scattering the surrounding rarefied material far off, creating a clear bubble around the star. Having traveled just a few light years away from the intense glare of the trapezium cluster, we encounter another remarkable stellar system, known as Theta 2 Orionis. This system does not stand alone. It is comprised of 3 distinct stars that are gravitationally bound to one another, dancing through space in a complex orbital ballet. These stars are located in close proximity to a fascinating structure called the Orion Bar. To visualize this, imagine an immense diagonal ridge of dense gas and dust, sculpted by the intense ultraviolet radiation from the nearby massive stars. It acts almost like a cliff edge in space, where the harsh radiation creates a boundary of hot gas emitting a brilliant light. For a very long time, it was virtually impossible for astronomers to study this specific area in any meaningful detail. The view was obstructed by thick, impenetrable curtains of interstellar dust that blocked visible light. However, the technological leap provided by the James Webb Space Telescope has changed everything. By observing in the infrared spectrum, which passes through dust like light through fog, more detailed and revealing images of this region have been beamed back to us, unveiling secrets that were previously locked away. The primary member, or the first component, of the Theta 2 Orionis system is a massive star in its own right. While it is just slightly less massive and not quite as luminous as the biggest star in the trapezium cluster we observed earlier, it is still a cosmic giant. Measurements of its surface temperature indicate it burns at approximately 35,000 Kelvin, making it blazing hot and bluer than our Sunday. The second component of this triple system is also formidable, measuring 15 times as massive as our Sunday. In terms of brightness, it is roughly 12,000 times as bright as the star at the center of our own solar system. The third and smallest component is still significantly heavier than our sun, weighing in at 5 solar masses, with a surface temperature that almost reaches 14,000 Kelvin. However, in the era of modern astronomy, it wasn't just the bright, massive stars that caught the researchers' attention. The sophisticated infrared cameras aboard the James Webb Telescope allowed it to detect previously unseen objects hidden deep within the cocoon of clouds and gas. Thanks to this piercing gaze, about 180 specific structures known as proplets have been discovered right at the heart of the Orion Nebula. The term proplet is short for protoplanetary disk. These are dense, dark disks of gas and dust surrounding young stars that are still in the active process of formation. They are the embryos of future solar systems. One of the most intriguing of these objects is cataloged as Orion 294-656. This specific object is a nascent star, estimated to be only about 1 million years old, an infant in cosmic terms. It is surrounded by a sprawling gas and dust disk that measures about 300 astronomical units in diameter. To put that in perspective, 1 astronomical unit is the distance from the Earth to the Sun, so this disk is 300 times wider than that distance. Thanks to its orientation relative to Earth, we can observe its structure and size with remarkable clarity. It appears as a dark silhouette against the bright background of the nebula. It is expected that this object will fully condense and hit the main sequence phase, the stable period of a star's life, in a few million years. When it does, it will likely be accompanied by a fully formed system of several exoplanets and possibly their orbiting satellites, created from the material in that very disk. If we allow ourselves a moment of scientific speculation, the night sky of these future celestial bodies would be a truly fantastic sight. Because they are forming inside a dense nebula, the sky would not be black. Just imagine a multicolored, luminous veil stretching across the firmament, glowing with the ionization of hydrogen and oxygen. Through this veil, the glow of a multitude of close and bright stars, far more numerous and brilliant than those seen from the Earth, would pierce through. And now and then, tremendous swirls of glowing gas would cover half the sky, turning the night not into darkness, but into a translucent, ethereal twilight. If we fly a little further out to examine the wider region, the texture of the environment changes. We see that the bulk of the nebula is filled with scattered gas. The central part of the cloud is filled with highly ionized hydrogen. This gas is in a high energy state because it actively absorbs the fierce high energy radiation from the massive stars nearby. The temperature of this gas can reach 10,000 Kelvin, but as we move away from the energetic center, the temperature falls sharply towards the edge of the region. These drastic contrasts in temperature and pressure, combined with the collision of powerful stellar wind streams, set the material in space into chaotic motion. This creates tremendous currents, shock waves, and vortices. According to calculations, some of these gas currents can reach speeds of up to 50 kilometers per second, a velocity far exceeding any storm on Earth. Furthermore, the physical size of these turbulent structures can be greater than our entire solar system. In some quieter areas of the nebula, astronomers have detected thin strands stretching for several light years. These filaments consist of relatively cool molecular hydrogen gas that has not been ionized, mixed with chemical compounds like methane, ethane, and even water molecules. Further out still, we observe that the bright central region of the Orion Nebula is actually enveloped in a vast, encompassing cloud of cooler, denser gas. Here, the visual interplay is stunning. The cloud of bright stars and the luminescence of the ionized hydrogen intricately intertwine, creating a beautiful, multicolored curtain of light. Hidden behind this curtain are hundreds of space objects that are completely invisible in the optical range, the range of light our eyes can see. However, the infrared cameras of today's telescopes allow us to peer through this veil of interstellar matter. By combining data from different sources, astronomers have discovered about 700 protostars at different stages of evolution buried within this region. Their concentration is noticeably lower than in the central part of the nebula. This is likely due to the lower degree of gravitational compression of the interstellar gas in these outer zones. The absolute majority of these hidden objects are very young by space standards and are still in the deeper process of formation. According to modern concepts of stellar evolution, new stars form during the gradual gravitational compression of large clouds of interstellar gas. Typically, as a result of this process, a giant nebula does not just collapse into one ball, but splits up into a number of closely grouped gravity centers. These centers attract more and more matter, eventually turning into protostars. Such clusters are called stellar nurseries, or more scientifically, regions of star formation. At a certain point in this process, the internal pressure of the compressed, heating gas pushes outward enough to compensate for the inward pull of gravitational forces. This brings the protostar to a state of temporary equilibrium. The remaining material that hasn't fallen into the star swirls into a giant vortex disk. Some of this material eventually spirals in and is absorbed by the future star, adding to its mass. By contrast, a significant portion of the material is expelled far beyond the boundaries of the nascent system. The growing magnetic field of the young star also plays a crucial part in this dynamic. Ionized particles accelerate through the star's twisting magnetic field lines and then rapidly escape from the vicinity of the object in the form of powerful jets. It has been calculated that such outflows can reach speeds of up to several hundred kilometers per second. As these high-speed jets slam into the slower, denser gas clouds surrounding them, they create large-scale vortices and glowing shock waves shaped like hemispheres. These distinctive structures are called Herbig-Haro objects. In the process of this violent collision, part of the kinetic energy dissipates into light and heat, giving these bizarre structures different colors depending on the gases involved. In addition, the ultrafast motion affects the surrounding material, spreading shock waves across it like ripples in a pond, which, incidentally, are also captured by telescopes. Since stellar nurseries contain many closely spaced protostars, each producing several gas emissions and jets, it is not surprising that Herbig-Haro objects exhibit an amazing variety of shapes and colors. They are clearly, essentially, the result of a major cosmic collision. Because they depend on the active jets of young stars, they are highly unstable and variable phenomena. Herbig-Haro objects rapidly change color and shape, evolving on human timescales, and typically disperse completely over several tens of thousands of years. During this relatively brief time, they cover a distance between 1 and 3 light years on an escape trajectory from their parent stars. About 400 such objects have been discovered so far, with their total number within the Milky Way estimated to be about 150,000. Perhaps one of the most violent varieties of this awe-inspiring natural phenomenon is a feature known as the bullets. These are dense clumps of gas, hundreds of astronomical units in diameter, that have also been detected in the Orion Nebula. Moving at incredible speeds, they easily pierce through thinner hydrogen clouds, creating far-flung shock waves in their wake, much like a supersonic aircraft creates a sonic boom. According to spectral analysis, the frontal parts, or the tips, of these objects contain atoms of iron that glow brightly in the infrared spectrum due to the friction and heat. The bullets are estimated to be about 1,000 years old, and their exact origin is still a mystery. They supposedly originated from some catastrophic, explosive event deep within the cloud, that launched them outward like shrapnel. Moving on from these specific details, we will soon find that the Orion Nebula is just one small part of a much larger cosmic structure called the Orion Cloud Complex. This massive assembly of molecular clouds stretches for hundreds of light years, accounting for virtually the entire constellation of Orion in the Earth's night sky. This is where the well-known Horsehead Nebula is located. This object is remarkable for its bizarre shape, which, as the name suggests, resembles the head of a horse. It is essentially a dense, dark dust cloud about 3.5 light years in diameter. It is not luminous itself. Rather, it is clearly visible because it blocks the light from behind it, appearing as a silhouette against a background with a contrasting scarlet glow coming from ionized hydrogen gas. Also close to the Orion Nebula, there is an impressive cosmic structure called Barnard's Loop. This is a faint emission nebula, roughly 300 light years in size, that forms a large arc across the constellation. It came into being about 3 million years ago. Its origin lies in a series of consecutive explosions of mutually close supernovae. After the shockwaves from these dying stars compressed the gas and the jets mixed together, they produced a gigantic, curved nebula. The glow of several young stars gathered in an open cluster illuminates this loop, making it reddish in hue. For all its beauty and grandeur, the Orion Nebula is a fragile and unstable object by the universe's standards. It is a temporary phase. The relentless stellar winds and the immense pressure of light radiation from the many young, massive stars, as well as the gas emissions and turbulent vortices, are constantly dispersing its material into the surrounding space. The nebula is evaporating from the inside out. It has already lost about 60% of its original material. In about 100,000 years, it will be stripped of its remnants entirely. In place of the shiny, multicolored cloud we see today, there will remain an open star cluster, very similar to the famous Pleiades. For a time, the young stars forming it will move together as a family, bound by their mutual gravity. But eventually, the gravitational pull of the galaxy will loosen their bonds, and each will find its separate way through the vast expanse of the boundless galaxy around. While many stars drift peacefully through the galaxy, some face a destiny that is far more dramatic and shrouded in darkness. It goes without saying that to detect a celestial object that absorbs absolutely all light shed upon it is a challenging task, to say the least. It is like trying to find a black marble on a dark floor in a room with no windows. That is the primary reason why there are not that many confirmed black hole candidates in our catalogs today. Despite the difficulty in seeing them, mathematical modeling and advanced simulations show that their number in our galaxy is not small. It may reach 100 million. This may seem like an incredibly big number on its own, but we must view it in context. Since there are estimated to be between 200 billion and 400 billion stars in the Milky Way, it makes us realize that in all these vast expanses, black holes are actually rare objects that one doesn't come across that much. In our journey through the cosmos, we must understand how such a dark object comes to be. A star, specifically the progenitor of a black hole, cannot just be any average star like our Sunday. It has to be truly massive, having a mass of at least 18 to 20 solar masses. Only a star of this immense weight possesses enough gravitational energy to trigger the final collapse. When such a star reaches the end of its life, it does not fade away quietly. It explodes. This ensures a powerful enough supernova event to compress the scorching hot core of the star inward. The pressure is so intense that it crushes atoms, squeezing the core into an exceptionally dense clump of material. After this catastrophic collapse has occurred, the density becomes infinite. Nothing in the universe, not even particles of light traveling at the fastest speed possible, will be able to stand up to the object's gravity force and escape. They are trapped forever beyond the boundaries of a conventional sphere predefined by the so-called Schwarzschild radius. This radius marks the point of no return. What used to be a brilliant, shining star transforms into a bizarre object with an inner makeup that would defy description by the physical laws we are familiar with. One of the most intriguing examples of such an object is referred to scientifically as A0620-0-0, also known as V616 Monocerotis. It is one of the black holes closest to our Earth that we know of currently. It lies approximately 3,300 light-years away from our planet, located in the constellation Monoceros, also known as the Unicorn. Unlike a solitary wanderer, this black hole forms part of a binary star system. It is locked in a gravitational dance with a partner. The other object in the system is an orange dwarf star, a star that is smaller and cooler than our Sun, with a mass about half that of the Sunday. The relationship between these two is intense. The orange dwarf is whipping around its dark companion at a breakneck speed. Every 7.7 to 5 hours, it completes a full orbit around an invisible object of unknown nature. By studying the motion of the visible star, astronomers can weigh the invisible one. Estimates show the mass of this invisible object to be around 6.6 times that of the Sunday. This mass is a crucial clue. It is admittedly too much for it to be a neutron star, which is another type of dense stellar remnant that typically tops out at around 2 or 3 solar masses. This leads one to believe, with a high degree of certainty, that the bizarre invisible object is more likely than not a black hole. This system is not peaceful. The invisible monster is feeding. In addition to getting deformed and elongated into an egg shape by the more massive neighbor's gravity, the orange dwarf is also actively getting stripped of its material. The black hole's gravity pulls on the star's surface, tearing away its outer layers of stellar matter. This material does not fall straight in. Instead, spiraling streams of scorching gas gradually flow toward the black hole, swirling around it like water going down a drain. This swirling matter forms a structure known as a bright accretion disk. As the gas spins closer to the black hole, friction causes it to heat up to millions of degrees, causing it to glow brilliantly in X-rays and visible light. It is thanks to this dazzling disk, which acts like a neon sign pointing to the invisible gravity well, that the black hole was detected in the first place. The region of space around V616 is crowded. There are at least several dozen stars in the immediate environs of this system, some of which almost certainly have their own planetary systems. Given the chaotic motions in such a cluster, it is highly likely that in the distant future, one of these stars will get dangerously close to the black hole. If it crosses a certain threshold, it will be captured. As a result, it will be sucked in by the object's insane gravity. This unfortunate star will have no choice. In this case, the same slow demise is eventually awaiting the black hole's new companion as that of its current one, a gradual stripping away of its lifeblood until nothing remains. The process of interaction of a black hole with other objects largely depends on their mass ratio and proximity. The smaller the distance between them and the more massive the black hole, the stronger the influence of its tidal forces over its companion. Tidal forces arise because gravity pulls harder on the side of the object closer to the black hole than on the far side. The star may be deformed by them, stretched out towards the system's common mass center. In extreme cases, these forces can open up streams of matter, forming channels that would carry stellar matter closer to the black hole, adding up to its accretion disk. If the tidal forces happen to be strong enough, they may well destroy the object completely before it even reaches the event horizon, turning it into a fiery ring of debris orbiting the dark center. This brings us to a fascinating question. Can worlds exist here? It is assumed that there may be planets orbiting a black hole, just as if it were a regular star. This concept challenges our intuition. In contrast to a widespread opinion often seen in science fiction, black holes are actually not able to suck in all objects around them indiscriminately, like a cosmic vacuum cleaner. From the point of view of gravitation, in astronomical terms, they behave just like any star with the same mass. If our sun were magically replaced by a black hole of the exact same mass today, Earth would not get sucked in. It would continue to orbit in the exact same path, just in total darkness. That is why, incredibly though it may seem, a black hole may well have a stable planetary system. There are several theoretical ways for such systems to form. Firstly, new celestial objects may originate in the aftermath of the star's death. When the progenitor star explodes as a supernova, it expels vast amounts of gas and dust. Some of this material may not escape completely, but instead settle into a nebula of gas and dust surrounding the new black hole. Influenced by gravitation, this dust begins to clump together. They first form clumps of material that collide with each other and attract more cosmic dust. As a result, over millions of years, they eventually turn into planets and satellites, as well as large numbers of small celestial objects, like asteroids and comets. But where would they get their energy? The black hole itself emits no light. However, the radiation of the black hole's accretion disk, that swirling ring of hot gas we discussed, may be powerful enough to warm them. It could provide enough heat to keep water liquid and even melt ice on their surfaces. Hypothetically, a planetary system like that, bathed in the glow of the feeding black hole, could be favorable enough for life to originate and, with any luck, evolve in this strange environment. Secondly, there is the scenario of capture. When a black hole captures and destroys another planetary system, the chaos can lead to survival. Some of the system's objects, instead of being consumed, may get flung into new orbits and choose to take up stable orbital positions around their new host. Of course, this makeover would bring about dramatic changes on the celestial object's surfaces. The radiation environment would change, and the gravitational stresses would shift. Thus, a frozen ice giant similar to Neptune might melt under the heat of the accretion disk and transform into an ocean planet, a world completely covered in water. Conversely, a massive gas giant might get stripped of its outer layers by the stellar winds from the disk, losing almost all of its hydrogen and turning into a Chthonian planet, essentially the exposed, rocky core of a former giant. Thirdly, the universe is full of drifters, space wanderers like rogue planets or interstellar asteroids, which have been ejected from their home systems, travel through the dark void. These wanderers may also be ensnared by the massive object's gravity if they pass too close. Even though systems like that have not yet been discovered in practice, the physics supports the idea. There is no reason to suppose they are non-existent. However, living near a monster comes with supreme risks. Balance is key. If, on the other hand, a planet is too close to the system's center and the black hole is massive enough, other destructive factors come into play. It is not just about gravity, it is about the environment. A scorching hot stream of material forming the accretion disk is like a sandblaster. It will strip the celestial object of its atmosphere, leaving it defenseless. Furthermore, the planet moving through any diffuse gas will experience drag. Its friction will slow it down, As it loses orbital speed, gravity wins, and it will pull it still closer to the black hole. Eventually, the planet reaches a critical limit. The extremely powerful tidal forces will overpower the planet's own gravity, holding it together. The difference in pull between the planet's front and back will become so great that it will rip the planet to tiny shreds. It is a violent, silent end. The debris rocks, water, gas will be pulled into the accretion disk. There, it joins the swirling river of matter and will gradually melt in the hot gas around. In the end, the remains of the world will inevitably get swallowed up by the black hole and, in essence, become part of it. To understand the full scope of these dark giants, it is posited by astrophysicists that there are three main types of black holes to be found in the universe. While they all share the defining characteristic of an event horizon, they are different first and foremost in terms of their mass and their origin stories. The first type dominates the cosmic landscape in terms of sheer scale. These can be found residing in the chaotic, dense center of most spiral galaxies, including our own. These are the supermassive black holes, truly gargantuan objects with masses reaching several billion solar masses. The formation of such titans is a direct result of their environment. The density of matter in the central part of a galaxy is generally extremely high. Stars do not drift in isolation here, but are packed together in tight clusters. This is the reason why there originates a big number of large and bright stars in these regions. As these massive stars rapidly burn out and die, they transform into black holes. Because they are so close to one another, these black holes do not remain solitary. They gravitationally interact, collide, and often merge with each other. As a result of this relentless cosmic cannibalism, supermassive objects are born. These monsters are often surrounded by giant accretion disks made of scorching hot material, spinning so fast that friction heats it to incredible temperatures. They illumine space so brightly that it makes them seen from billions of light years away, appearing as beacon-like objects known as quasars. Remarkably, we can detect these beacons even if the rest of their host galaxy is too faint to be observable to us. The second type of black hole is much more widespread throughout the galactic disk. But at the same time, black holes like these are not that easily detected because they lack the blinding brightness of a quasar. These are the stellar mass black holes. Their masses are typically close to those of stars, ranging from about 5 to perhaps 100 times the mass of the Sunday. They form directly out of large stars at the end of the latter's life cycle, following the supernova explosions we discussed earlier. Once formed, they are not static. By devouring other nearby celestial bodies and siphoning off interstellar gas, these objects gradually gain in size. Over eons, they eventually turn into intermediate mass black holes. Furthermore, just like their supermassive cousins, they can also merge together. When two stellar black holes spiral into one another, the collision is so violent that it generates gravity waves, ripples in the fabric of space-time itself that distort space for many light years around, a phenomenon we can now detect with sensitive instruments on Earth. The third type is the most elusive and intriguing, the hypothetical primordial black holes. Unlike the others, these did not form from the death of stars. Their existence has been inferred from today's leading theories of the universe's origins and evolution. In the fractions of a second after the Big Bang, the universe was not perfectly smooth. There were fluctuations in matter and density. These tiny pockets of ultra-dense matter that filled space in its early stages of evolution may have been favorable for black holes of infinitely small size to originate purely from the crushing pressure of the early cosmos. It should be mentioned that, According to the principles of quantum mechanics proposed by Stephen Hawking, black holes are not truly black, they leak radiation. According to estimates, the smaller an object of this type is, the faster it evaporates. At the end of its life cycle, as it loses the last of its mass, it turns into a tremendously powerful electromagnetic impulse, essentially exploding. Modeling shows that primordial black holes with masses around 10 to the power of 12 kilograms, roughly the mass of a mountain, are supposed to be flaring up and expiring sometime around now. But to date, no such event has been officially registered yet, keeping their existence in the realm of theory. There is also a subcategory worth noting. According to a certain hypothesis in particle physics, a microscopic black hole may form during the collision of extra-high energy elementary particles. This variety is referred to as quantum black holes. However, do not worry about experiments creating them. The energy conditions necessary for such an event to happen are impossible to be reproduced in laboratory conditions on Earth. Furthermore, the estimated life expectancy of these hypothetical objects is so small fractions of a fraction of a second that it can hardly be measured with today's latest and most advanced methods. That is why quantum black holes still officially exist only in the theory of complex mathematics. Of course, distinguishing between reality and theory is hard because it is extremely difficult to detect such dark and compact objects against the black background of space. Since we cannot see them directly, we look for their influence. Some of them happen to have a star companion whose motion betrays the presence of the hidden giant. The star's anomalous trajectory of movement, swinging back and forth as if dancing with a ghost, gives telltale signs of there being an invisible thing in close proximity. Another popular method of detection is the observation of accretion disks. Even if we cannot see the hole, the light from the hot gas swirling around it is distinct. These objects' spectra, the breakdown of their light, have some typical features that allow astronomers to tell them apart from other sources of light in space. Sometimes, with high-resolution radio astronomy, we are lucky enough to get a snapshot of a glowing disk with a black spot in the center. That shadow is direct evidence that the observed object's structure is quite unusual. A black hole may also be detected thanks to the gravitational microlensing effect. This technique relies on chance alignment. It involves detecting the massive invisible object as it transits precisely between the Earth and a remote background star. The black hole's gravity acts like a lens, bending and magnifying the light of the background star. This changes the star's brightness and spectrum in a special, predictable way. But, admittedly, this method requires a number of rare factors to successfully work, as the alignment must be perfect. There is hardly any doubt that space is filled with great numbers of objects that are dark and not easily noticeable. There may be wandering black holes among them, ejected from their home clusters. These mysterious objects, roaming around in interstellar space and absorbing every bit of light they come across, will probably never reveal their secrets to us unless they pass very close to something that lights them up. While the darkness holds its mysteries, the visible universe is equally baffling. Usually, when we scan the cosmos, it is the potentially habitable planets with favorable conditions and a moderate climate that especially catch one's attention. We look for blue marbles like Earth among the great diversity of other worlds out there. Or else, on the contrary, extremely dangerous objects like the black holes we just discussed stand out among others. Still, there is yet a third category of discovery that fascinates astronomers. It is the anomalous celestial objects manifesting unusual behavior, which is barely scientifically accountable at first glance. Objects like that challenge our knowledge of how planetary systems should work and deserve special attention. This is exactly the kind of world we will be looking at now. Let us travel back to the year 2009. We are looking at the environs of the Kepler 413 system. Located roughly 2,300 light-years away, an unknown object passes between our planet and a distant star, briefly reducing its luminosity. Astronomers, monitoring the brightness of thousands of stars, take this event to be a standard exoplanet transit and announce the discovery of a new celestial body. High-precision calculations based on the dimming of the light even make it possible to determine its parameters. The planet turns out to be a cool giant, likely a gas planet, with a mass of about 25 times that of the Earth and a radius of about 40% that of Jupiter. However, the orderly, predictable clockwork of the universe seemed to break down. 180 days later, when the planet was calculated to complete its orbit and cross the star again, another expected transit never occurred. The planet, so clearly visible in the old data, seemed to have vanished without a trace. This baffled the team. A dark spot in the photosphere of the star, a sunspot or a giant dust cloud moving in its vicinity, would have accounted for the mysterious phenomenon, mimicking a planet. But these hypotheses were dispelled when, 800 days later, the mysterious object reappeared just as suddenly as it had vanished. The hypothetical planet eclipsed the disk of its parent star 5 times in rapid succession before disappearing again for a long period. This pattern was baffling until the dynamics were modeled. Still, the key to the riddle had been found. It turned out that Kepler 413b has a highly unusual orbit. The celestial body is not orbiting a single star, but is located near a binary star system, 2 stars orbiting each other. It sits about 36 astronomical units from the system's common mass center. Because it orbits 2 moving targets, its trajectory is constantly affected by gravitational perturbations. The constant change in the gravitational pull of the 2 nearby stars shifts the orbital plane considerably. Imagine a spinning coin that is wobbling before it settles. The planet's orbit wobbles like that, causing cyclic oscillations. When the deviation reaches its maximum, the object tilts so far that it leaves our line of vision from Earth, passing above or below the star relative to us, and then eventually returns to cross the face of the star years later. Calculations show that Kepler 413b's orbit also precesses, or wobbles, with a periodicity of about 11 years, deviating 2.5 degrees in each direction from its average value. But the chaos does not stop at the orbit. The planet's own axis of rotation also changes its position significantly, swinging wildly over short timescales. It has a maximum angle of inclination, or axial tilt, of up to 30 degrees. On Earth, our tilt is stable, giving us predictable seasons. On Kepler 413b, combined with the notable eccentricity of the orbit and its periodic shift, the climatic conditions on the surface change in a bizarre and violent way. The region that receives the most light from the parent stars is constantly shifting from the equator to the poles and back within a matter of years. This leads to dramatic variations in temperature across the planet's surface. It is likely that this process generates huge planetary-scale hurricanes driven by the rapidly changing heat distribution. These storms can be larger than the Great Red Spot of Jupiter. Powerful air currents can carry ice clouds at speeds of several kilometers per second, gradually becoming unstable and dispersing into the chaotic atmosphere. Meanwhile, the collision and deformation of these massive vortices is capable of causing tremendous atmospheric emissions. These are plumes of gas that have the power to overcome the planet's gravity and reach outer space. According to calculations, they will hang a while up there in the void before gravitational forces pull them back down. All these incredible phenomena make the planet a rather harsh, unpredictable place. However, even this chaotic world may seem like a tranquil, serene island in comparison to the following world we have discovered. We now move 190 light years from Earth to the environs of the HD 10606 system. At the center lies a yellow dwarf star, surprisingly similar in parameters to our own Sunday. But there, the similarity ends. This star is orbited by a planet with a highly variable climate driven by one of the most extreme orbits ever discovered. This planet does not circle its star. It dives at it. It whizzes towards its parent star as rapidly as a giant comet, swinging in from a great distance to skim the surface of the star, burning itself in the hot rays of its corona. Then, using that gravitational sling, it retreats far out to the cold periphery of the system. The object is a massive gas giant with a mass 4 times that of Jupiter and a radius slightly different from that of Jupiter. At the furthest point in its elongated, needle-like orbit, the planet is approximately 0.8 to 8 astronomical units away from the parent star. At this specific distance, it resides in a temporary zone of comfort, receiving about as much heat from its star as the Earth does from the Sunday. It has been suggested by atmospheric models that this is the brief window when the planet's weather behaves somewhat predictably. This is when clouds consisting of water vapor droplets, ice crystals, or even microparticles of quartz may condense in its upper atmosphere. For a short time, the temperatures on the surface of the hypothetical satellites of this gas giant could be moderate, perhaps even comparable to those on Earth. But this tranquility is a deception. As the planet conserves angular momentum and swings back towards the star, conditions on it change very quickly, spiraling into violence. Within just 55 days, the distance between the planet and the star shrinks by a factor of nearly 30. As it dives inward, the energy flux, the raw amount of radiation blasting the planet, increases by a factor of 800. Observations and computer simulations show that at the lowest point in its orbit, known as the periastron, the exoplanet's temperature undergoes a catastrophic spike. It roughly doubles within a matter of just 6 hours, rocketing from 500 to 1,200 degrees Celsius. This is not a gradual warming. It is a thermal explosion. The atmosphere simply cannot absorb and redistribute this sudden injection of energy peacefully. Such drastic changes result in violent hurricanes and jet streams, which can reach speeds of up to 5 kilometers per second, that is faster than the speed of sound. By absorbing an incredible amount of heat in such a short time frame, the atmosphere on the sun-facing side of the gas giant expands so fast that it produces tremendous shockwaves. These acoustic booms are capable of sweeping across the entire planet multiple times, carrying the heat to the night side. In this hellish environment, chemistry behaves strangely. Water vapor is broken down into its constituent atomic parts, oxygen and hydrogen, by the sheer ferocity of the temperature. The delicate clouds of quartz crystals that formed weeks ago evaporate without a trace, turning back into gas, only to recondense into gigantic sand clouds later as the planet retreats and cools. In all likelihood, HD 80606b is the only planet in its system. The gravity of another nearby star has not only warped its orbit into this extreme shape, but has also likely wreaked havoc on the original protoplanetary disk, ejecting any other siblings. So, the chances of encountering other large objects nearby are rather slim. However, while some worlds are destined to be lonely wanderers, others are locked in a dangerous, crowded dance. Destabilization of a planetary system due to the interaction of celestial bodies is not uncommon. To see this, we travel 1,530 light years from Earth to the environs of the Kepler-36 system. The central object in this system is a yellow subgiant star. It is an older, more evolved version of a star similar to ours. Its mass is comparable to that of the Sun, but it has swollen with age, so its radius is 62% larger than that of our star. There are two planets rapidly orbiting this expanded star, a rocky super-Earth and a hot mini-Neptune. What makes this system unique in the annals of astronomy is their proximity to one another. Their orbits are nested incredibly close together. Every 97 days, they experience a planetary conjunction where they mutually approach at a critical distance of only 1.9 million kilometers. In the vastness of space, this is virtually touching. To put it in perspective, this is about 20 times less than the minimum distance between the Earth and Venus. At such moments of close encounter, their mutual attraction causes global cataclysms. They tug at each other with immense gravitational force, but after a few days, the celestial bodies diverge again until the next resonance occurs. According to calculations, the gravitational interaction between the planets at the point of closest approach is about 13 times higher than the tidal pull between the Earth and the Moon. In particular, this destructive tidal effect should be seen vividly on the surface of the rocky planet, the inner of the two worlds. Under the influence of these titanic forces, the planet does not just experience high ocean tides. The solid ground itself deforms. Its crust may crack and shift, causing planetary quakes of incredible power that would shatter continents. The resulting chasms from these quakes may be hundreds of kilometers long. The internal friction generates massive amounts of heat, likely causing multiple eruptions of gigantic volcanoes simultaneously. It is likely that some regions of the planet do not have time to cool down in the short period of relative tranquility between approaches, creating permanent seas of eternally bubbling red-hot magma. The reasons for the formation of such an unusual, tightly packed system are still debatable among astronomers. We now know that the super-Earth, officially dubbed Kepler-36b, is located just 0.115 astronomical units away from its parent star. It moves rapidly, taking only 14 days to complete a full orbit around it. The super-Earth's mass is 4.5 times that of the Earth, and its radius is 1.5 times that of our planet. Based on its distance from the subgiant star, the object has been calculated to have an equilibrium temperature of roughly 980 Kelvin, or just over 700 degrees Celsius. Perhaps the most interesting detail is its density. It has an average density about 30% higher than that of the Earth, suggesting it is made of very heavy stuff. The data suggests that this celestial body could be what scientists call a Chthonian planet. This term refers to the theoretical remains of a gas giant that migrated too close to its star and lost its atmosphere, leaving behind only the naked core. Such objects contain many heavy metals like iron and lead, as well as sulfur and silicon compounds. It is likely that the light elements like hydrogen and helium that once made up the thick, dense shell of the celestial body may have been blown into space by the intense stellar wind of the subgiant star. Nor should we forget the influence of its neighbor. The second planet's gravitational pull could potentially have contributed to this stripping process, helping to peel away the outer layers of Kepler-36b. This second object is called Kepler-36c and is likely to fall into the class of hot mini-Neptunes. The celestial body moves in a nearly circular orbit just outside its partner, with a radius of 0.128 astronomical units, and completes a lap every 16 days. Its mass is 8 times that of our planet, and its physical size is significantly larger, with a radius 3.7 times that of the Earth. Because of its proximity to the star, the temperature of this object is also very high, estimated at 928 Kelvin, or 655 degrees Celsius. Unlike its rocky neighbor, this celestial body should be surrounded by a thick, multi-layered atmosphere, consisting mainly of nitrogen, hydrogen, and helium. As we go deeper down through this thick envelope, the pressure inside the gas shell increases dramatically. It does not have a clear surface like an ocean. Rather, the gas gradually thickens until it turns into an ocean of supercritical fluid, a state of matter that is neither liquid nor gas surrounding the solid core. Meanwhile, under certain conditions within this chaotic system, truly fantastic phenomena are also possible. For example, consider the satellites. If the smaller rocky planet ever had a moon, the gravity of the more massive planet nearby could potentially capture it during a close flyby. Or, even more dramatically, the intense tidal forces acting during the conjunction might exceed the structural limits of a moon, effectively destroying them to form vast asteroid streams or rings around the planets. In addition to these physical changes, the mutual gravitational pull of the two planets constantly distorts their orbits. They are not fixed on perfect tracks. They wobble. The gravity alters their eccentricity, how oval the orbit is, and other orbital parameters over time. Because of this constant tug of war, the entire system behaves chaotically and unpredictably. Mathematically, it is an n-body problem, meaning its evolution cannot be predicted with certainty over any extended period. Computer modeling shows a 91% probability that the orbital dance will eventually fail. The simulation predicts that the two planets will collide with each other over the next 70 million years. Such a collision would be an event of apocalyptic proportions, producing hundreds of thousands of pieces of debris. This cloud of rock and gas would disperse throughout the planetary system, thereby creating a still greater chaos within it, perhaps leading to the formation of a new, single, hybrid planet. Such tremendous cataclysms may have occurred more than once in the history of the galaxy, shaping the systems we see today. Leaving this chaotic future behind, we turn our eyes to another wonder. Located 434 light-years from Earth, we find a surprising object intricately called Super Saturn, or scientifically J1407b. It is located approximately 4 astronomical units away from a young, sun-like star. The classification of this object sits right on the boundary of our definitions. It is either a massive brown dwarf, a failed star, or a large gas giant. It is truly massive, estimated to be 20 times as heavy as Jupiter. Detailed observations reveal that this massive object is a remarkably young planet, estimated to be only about 15 to 16 million years old. In the timeline of the cosmos, it is merely an infant, still in the chaotic final stages of forming. Spectroscopic analysis suggests that most of its atmosphere consists of the primordial elements hydrogen and helium, likely shrouding a massive metallic core deep within its depths. However, what makes this object truly unique is not the planet itself, but what surrounds it. This object is spun by a colossal system of rings, superficially similar to Saturn's, but scaled up to a magnitude that challenges the imagination. The transit method, which analyzes the dipping light of the parent star as the planet passes in front of it, revealed a complex structure of at least 37 distinct rings. The scale is staggering. The largest ring's outer radius measures about 6 astronomical units. To put that in perspective, 6 astronomical units is roughly the distance from the Sun to the orbit of Jupiter. This means the ring system alone is comparable to the size of Venus's entire orbit around the Sun and is approximately 640 times the radius of Saturn's rings. According to calculations regarding the density and opacity of the material, the total mass of this circumplanetary disk is substantial, estimated to be bigger than the mass of the entire Earth. Unlike the orderly, stable rings of Saturn, this system behaves chaotically. Its behavior manifests signs of randomness and turbulence. Mathematical modeling shows that such massive structures are not dynamically stable over long periods and will gradually disintegrate. It is a transient masterpiece. Some of the rock and ice objects making them up lose velocity due to friction and collisions, causing them to fall inward to the central planet, while others, on the contrary, accelerate via gravitational slingshots and leave the disk forever, ejected into the void. However, this process of decay is greatly extended in time and may take several 100 million years to complete. Amidst this swirling chaos, order is beginning to emerge. A large rupture, or gap, with a radius of about 0.4 astronomical units was detected in the system of rings. In astronomy, a clean gap in a dust disk is considered indirect but strong evidence of the existence of an exosatellite, or a moon, forming in this region. This hypothetical moon is estimated to be about 80% the mass of the Earth, making it nearly the size of Venus. According to our current understanding of the physics of space objects, it is a kind of object capable of clearing its orbit. As it moves, its gravity acts like a broom, sweeping up or scattering small debris, thus forming a wide rupture in the ring structure. In addition to this large moon, observations suggest the presence of at least 2 more celestial bodies, each with a mass of about 30% that of the Earth, roughly twice the mass of Mars. These are located further out, at a distance of about 25 astronomical units from the center of the brown dwarf. Just like it is the case with the large gas planets known to us in our own solar system, it can be assumed that a total of several hundred exosatellites, including rather massive ones, may be located within the gravitational influence of the central object. A computer simulation of such a system creates a fascinating picture of a potential world. By including radiation from the distant parent star, the intense heat flow radiating from the cooling giant planet itself, and the friction from tidal influences, the model shows that the temperature of the celestial bodies making it up could approach comfortable values. This raises the possibility of liquid water. One can only imagine how enchanting the night sky would be from the surface of such an exosatellite. It would be a view unlike anything on Earth. At this distance, the brown dwarf, or super Jupiter, occupies 70 times as much space in the sky as the full moon does from Earth. It would hang there as a dominant, looming presence. Its soft, reddish thermal glow can dispel the darkness, ensuring the satellite never experiences true blackness, but rather turns the night into a permanent, misty twilight. Instead of the star-spangled canopy we are used to, the planet's sky is crisscrossed by vast swaths of light. From horizon to horizon, the giant rings reflecting the light of the parent star. However, beauty comes with violence. At the same time, the tidal forces of such a nearby massive body would be immense. As the moon orbits, the gravity of the giant planet would stretch and squeeze the satellite's core. This could provoke multiple eruptions of cryovolcanoes or magma on the satellite's surface. Furthermore, if liquid water exists, its hypothetical ocean would not be calm. The tidal pull could slam the land with giant waves kilometers high, sweeping deep inland twice a day. The width of a tidal zone under such conditions could reach hundreds of kilometers, making it a unique climatic and biological zone, something like a cross between dry land and the deep ocean floor, constantly shifting between the two. Still, it should be mentioned that such structures tend to be unstable and change their appearance quite quickly, beyond recognition on astronomical timescales. It is difficult to say how much longer the universe will be able to admire these giant rings and what they will look like in millions of years. As the system evolves, gravitational interactions often become destructive. This instability leads us to a broader, darker topic. Assumptions about the existence of space objects the size of a planet which are independent from any star have been around for a long time. Sometimes, the chaos of a young system like the one we just described ejects a world entirely. Such celestial objects, freely drifting around into the cold void of interstellar space, are referred to as orphan, free-floating, or rogue planets. Astronomical bodies of this kind are the ghosts of the galaxy. They emit very little thermal and light energy into the space around them, having no internal fusion and no nearby star to reflect. It is suggested that there are no bodies in their close proximity they could clearly interact with or be bound to. That is why it is hardly surprising that these objects are so difficult to detect. They are essentially invisible against the black background of the cosmos. The first potential representatives of this class of planets were spotted as recently as in the early 21st century. The detection methods are ingenious. The warmest rogue planets, those that are still young and retaining heat from their formation, can be detected with sensitive infrared telescopes. Others are found thanks to something called the gravitational microlensing effect. This phenomenon occurs when a dark planet passes precisely in front of a distant background star. The planet's gravity acts like a lens, briefly magnifying the star's light. By measuring this brief brightening, astronomers can infer the presence of the planet. As one would expect, this class of celestial objects is one of the most mysterious and understudied today. Because the alignment required for microlensing is so rare and brief, confirmation is difficult. Only 3 astronomical bodies can be classified as rogue planets with a sufficient degree of certainty, with the overall number of rogue planet candidates hovering around over 24. Incidentally, statistical analysis of data collected in the course of the OGLE project, the optical gravitational lensing experiment, suggests a staggering population. It indicates that the Milky Way may supposedly be home to up to 100 billion objects of this class. This number is comparable to the number of stars in the galaxy, implying that for every star you see, there may be a lonely planet hiding in the dark. This may only mean that right now we are at the very beginning of an upcoming series of discoveries in this field. Our notions of what rogue planets are like have long been based purely on assumptions and hypotheses. However, with the technological advancement of highly sensitive observation equipment, there arose opportunities to put them to the test in practice. The rogue planet lying closest to the Earth among those already confirmed is known as WISE 0855-0714. It is located just 7.2 to 7 light-years away from the Sun, making it one of our closest neighbors in the entire galaxy, closer even than Sirius. It was detected in 2014 with the WISE Orbital Infrared Telescope. The astronomical body cannot be seen through optical telescopes, as it emits no visible light to speak of. It is a world of eternal night. The reason for this invisibility is its extremely low temperature. Measurements indicate it ranges from 225 to 260 Kelvin, or approximately 48 to 13 degrees Celsius below zero. While this is freezing by human standards, for a deep space object far from any star, it is surprisingly warm, indicating it still retains heat from its birth. In terms of its parameters, it resembles a cooled-off gas giant, and its age cannot be under 1 billion years. The rogue planet is mostly made up of hydrogen and helium. However, in 2016, the Gemini Observatory produced evidence of something remarkable: the presence of large amounts of water in its atmosphere. Based on the temperature and pressure profiles, it is suggested that this water is condensed into clouds made up of the tiniest particles of ice. This was the first evidence of water clouds outside our solar system, painting a picture of a frozen, stormy atmosphere swirling in the dark. Today, it hasn't been established for certain how this object came to be alone in the void. There are currently two versions or leading theories suggested by researchers to explain the origin of rogue planets. According to the first version, a celestial object like that starts its life cycle normally in the protoplanetary disk of a regular planetary system. It forms alongside other siblings. However, solar systems are violent places in their youth. Mathematical modeling of this process shows that if the original cloud of gas and dust is heavy enough to form multiple massive gas giants, the gravitational tug-of-war between them becomes intense. It is highly likely that at least one planet will lose the battle and be ejected beyond the system. The celestial object acts like a billiard ball, struck by the gravity of a larger planet like Jupiter, and is flung out. A planet may also be forced out of its star's environs if another massive star passes it by too closely, stripping it away, or else if its planetary system collides with another system. The chances of specific events like a collision are admittedly comparatively small, but gravitational ejection is seen as a common outcome of planetary formation. The other version proposes a different origin story. It has it that the space object was born just like any other star, through the independent collapse and compression of a cloud of interstellar gas. In this scenario, it did not form around a star. It formed as a star would. At the same time, the mass of the object proved to be too small. It gathered enough matter to collapse into a sphere, but not enough to generate the immense pressure and heat required to unleash any thermonuclear reactions in its interior. It failed to ignite. It goes without saying that in this manner, it may turn out only as a gas giant or a brown dwarf, but not a rocky planet similar to the Earth. This distinction in formation leads to a debate in classification. Some researchers don't agree that these objects should be seen as rogue planets and classify them as sub-brown dwarfs instead. The line is blurry. Others suggest using the term planemo, a contraction of planetary mass object for all interstellar wanderers that don't show any thermonuclear activity regardless of how they formed. Bearing in mind today's notions of the makeup of brown dwarfs and gas giants, we may estimate the mass of WISE 0855-0714 at anything from 3 to 10 Jupiter masses. This mass is significant. It is huge for a planet, but small for a star. This rather falls short of the critical limit needed for starting a thermonuclear reaction of deuterium, which requires about 13 Jupiter masses. However, it is quite enough to create immense internal pressure, sufficient to keep the heat effectively trapped inside the planet for billions of years. Taking into account our expanding knowledge about natural laws and thermodynamics, we can scientifically predict what the conditions on such a lonely astronomical body's surface are like, even without seeing them directly. It was often assumed that without a star, a planet becomes a frozen wasteland instantly. However, According to research by planetary scientist David John Stevenson from the University of California in the US, this is not necessarily the case. His model suggests that gas giants similar to Jupiter do not cool off instantly after receding from their star. The physics behind this retention of heat is fascinating. A massive planet is essentially a giant thermos. Their thick atmosphere, composed primarily of hydrogen, is an extremely efficient insulator. This gas opacity prevents infrared heat from escaping rapidly into space. Deep inside, the conditions are even more extreme. The dense and hot nucleus, made up of metallic hydrogen, a state of matter where hydrogen is squeezed until it behaves like a liquid metal, can keep the planet heated for a considerable time. This internal heat comes from the energy left over from the planet's formation and the slow gravitational contraction of the world itself. Estimates show that the temperature of the lowest strata of such a hypothetical celestial object's atmosphere may be comfortable. In certain layers, the pressure and temperature balance could be high enough for liquid water to be around. Unlike on Earth, where oceans lie on rock, here, water would likely be present in the atmosphere as giant clouds made up of the tiniest droplets suspended in the high-pressure gas. These deductions agree with the results of detailed mathematical modeling of the object WISE 0855-0714 carried out by a team of scientists from the University of Edinburgh. Their simulation showed that the most likely temperature value of the planet's effective surface is approximately 250 Kelvin, or roughly 23 degrees Celsius below zero. While this sounds freezing, for a world in the void, it is remarkably temperate. Furthermore, the analysis suggests the celestial body's atmosphere also has a comparatively warm layer, roughly 100 kilometers thick. The density in this habitable layer fluctuates from 0.4 to 1.2 milligrams per cubic centimeter. Crucially, this density is comparable with the air conditions on the Earth at sea level. Because of this pressure and potential warmth, it is thought that this environment, despite being in eternal darkness, should be favorable for potential organic life, perhaps floating aerial microbes, similar to those theorized in the clouds of Venus. Incidentally, a planet does not have to be a massive gas giant to avoid freezing completely in the cosmos. The possibilities for rocky worlds are equally intriguing. In 2020, a compelling rogue planet candidate was detected using gravitational microlensing techniques. This object was given a long scientific designation, OGLE 2016 BLG 1928. It is still awaiting final confirmation of the rogue planet's status, and its parameters have been defined only generally so far according to preliminary data. However, the analysis of the light curve suggests the object is comparable to the Earth in terms of its mass. Its location is highly uncertain due to the nature of single-point microlensing. It is anything from 30,000 to 180,000 light-years away, possibly residing in the Milky Way's central bulge. According to our current scientific notions of planetary formation, an object with a relatively low mass like that is not supposed to be a gas giant. It does not have enough gravity to hold onto a thick hydrogen envelope. Therefore, it is more likely to be a rocky planet with a solid surface. This, in its turn, offers good grounds to believe that the object formed in the protoplanetary disk of a standard planetary system. As the latter was forming, the chaotic dance of gravity played out. This Earth-mass world may have been ejected from the system as a result of a cataclysm in space, such as a scattering event, or alternatively under the influence of a larger neighbor like a migrating Jupiter. After that violent exit, it was left to its own devices and so became a free-floating planet. What will happen to it next is predefined by a combination of several factors. The surface is almost certainly frozen solid. However, provided the object's atmosphere is sufficiently dense, it will be reliably thermally isolated. Even without an atmosphere, a thick layer of ice on its surface could produce the same isolating effect. Ice is a poor conductor of heat. It acts like a blanket, trapping the planet's internal warmth. In addition, with the object's interior scorching hot from formation, and with radioactive elements like uranium and thorium undergoing decay in the mantle, heat is constantly being generated from within. Therefore, scientific models suggest that deep beneath the frozen crust, most of the hypothetical ocean will remain in a liquid state. It would be a pitch-black, high-pressure global ocean, similar to the environments we suspect exist on Europa or Enceladus in our own solar system. Furthermore, if the planet happened to have a moon that remained bound to it during the ejection, which is rare but possible, it may have obtained a secondary heat source. If this is the case, tidal forces from the moon's orbit are likely to continue to deform and warm up the lithosphere through friction. Theoretically, in these warm, mineral-rich abysses, with any luck, primitive anaerobic life forms may have stayed around. These organisms would rely on chemosynthesis rather than photosynthesis. Although, of course, without a way to visit, it would be next to impossible to discover their traces now. Most of the data about the rogue planets we know today were arrived at following mathematical modeling and complex calculations rather than direct imagery. It was possible to do these calculations thanks to the tiny bits of information gleaned with the help of orbital and Earth-based telescopes. To improve this, astronomers are constantly proposing new missions. Even as I speak, a project is being worked on, known in some proposals as Cleopatra or chemically distinct mapping missions, similar to the Roman Space Telescope. Its main objective will be to search for free-floating planets and other dark objects in space with the subsequent precise definition of their parameters. The project relies on a sophisticated technique called microlensing parallax. As we discussed, microlensing is a phenomenon when a celestial body passes between a remote star and the observer on the Earth, and briefly interferes with the light emitted by the remote star in the background, acting like a lens. However, a single observation only tells us something passed by. It doesn't easily tell us how far away or how massive it was. This is where parallax comes in. When the same event is observed from different angles, for instance, from a telescope on Earth and a spacecraft millions of kilometers away, the geometry changes. The moment of transition, the peak brightness, will be registered a fraction of a second, sooner or later, in one observatory than in another. This difference is referred to as lensing parallax. This effect allows scientists to use triangulation to gauge the exact distance to a detected object, as well as its mass and dimensions with much higher precision. To achieve this, an interplanetary spacecraft is planned to be created within the scope of such projects. It is supposed to blast off the surface of the Earth, potentially utilizing launch windows similar to those used for missions to Mars, after which it will enter its own distinct orbit around the Sun, separating from Earth to create a wide baseline for observation. The project will likely be aided by a specialized artificial intelligence component. The volume of data from monitoring millions of stars is immense, and the AI's mission will be to process and analyze collected information in real time, flagging potential lensing events for immediate follow-up. The Cleopatra or Kartra project concepts will certainly delight us with a wealth of exciting and important information in the coming decades, so there is a lot to look forward to. But ultimately, what is to become of all those rogue worlds out there? we must confront the reality that they are drifting quite by themselves in the dark depths of the universe. In theory, an orphan planet may be captured by the gravitational field of a star it passes close to and become part of its planetary system. This would be a cosmic adoption, but the physics of such an event requires very specific speeds and angles. This chance is, by all accounts, minuscule. Most objects like that are destined to wander for billions of years through endless expanses of space. They are the silent travelers of the galaxy. While their cores will stay warm for eons, they are slowly and inevitably cooling off. Eventually, in the unimaginably distant future, they are likely to be swallowed up by black holes that sweep through the galaxy, or else destroyed as a result of a rare cataclysm in space. They will fade into the background radiation, likely never to reveal their secrets to mankind. Leaving these small, lonely worlds behind, we expand our view to the structure of the cosmos itself. The distances from the Milky Way to other galaxies are, by all accounts, mind-boggling. As a rule, the distance to our neighbors is measured not in kilometers, but from millions to billions of light years. Here, we encounter a fundamental rule of the cosmos. Due to the universe's cosmological expansion, space itself is stretching. Consequently, the distance between the Earth and any remote object in the universe is constantly growing. This expansion affects the light traveling through that space. As the space stretches, the wavelengths of the light are stretched with it, shifting them towards the red end of the spectrum. This makes the light emanating from this object look redder than it actually is. This phenomenon is known as a redshift. It is distinct from the Doppler effect caused by local motion. This is the expansion of the fabric of reality. It is of great help to astronomers, acting as a cosmic ruler for gauging distances and velocities on the astronomical scale. While the vast majority of the cosmos is racing away from us, stretching the light into the red spectrum, there are rare exceptions to this rule. Alternatively, some galaxies' spectrum is blue shifted. In the language of physics, this shift to the shorter, bluer wavelengths means that they are not on an escape trajectory from us, but on the contrary, are moving through space to meet us. One of these unusual space objects is the galaxy M86, located in the dense and chaotic Virgo cluster. This cluster is a massive collection of galaxies, roughly 52 million light-years away from the Sun. Unlike its neighbors, which recede with the expansion of the universe, M86 is moving towards the Milky Way at a breakneck speed of around 244 kilometers per second. This incredible velocity makes it one of the fastest moving blue-shifted galaxies observable from Earth. However, moving at such speeds comes with a cost. The space between galaxies in a cluster is not empty. It is filled with a thin, hot medium of gas. By moving at high speed through this scattered gas, M86 experiences a powerful headwind, a phenomenon astronomers call ram pressure. Just as a strong wind blows back the hair of a cyclist, this pressure is constantly stripping M86 of its own interstellar matter. As a result of this violent process, it leaves a trail of long lines of warm ionized hydrogen behind it, marking its path through the cluster like the wake of a ship. But the history of M86 is not just one of speed, it is also one of violence. Detailed imaging reveals that M86 is connected with the almost destroyed spiral galaxy NGC 4438 via several of these gas filaments. The bridge of matter suggests a dramatic history. These two galaxies are thought to have collided at some point in the distant past. It was a high-speed hit-and-run, which was the smaller one's undoing. stripping it of its structure. Interestingly, M86 is known to have destroyed its other neighbors in the past as well. It is a galactic cannibal. Several faint, stellar streams, ribbons of stars wrapping around the galaxy have been detected in its outer halo. These are likely to be the digested remains of smaller galaxies absorbed earlier in its history. Furthermore, an impressive number of globular clusters, dense spherical collections of ancient stars in its structure, is another outstanding feature of M86. Observations show that their number is upwards of 3,800. To put this in perspective, this is around 25 times as many as are found orbiting our own Milky Way. There is a theory that claims these extra clusters are the leftovers or the nuclei of dwarf galaxies that M86 would have absorbed in the past. If it really is the case, then this giant would have destroyed tens or even hundreds of other galaxies to reach its current size. Having said that, in the grand zoo of cosmic oddities, M86 looks anything but unique. The galaxy ESO 137-001, which we will be looking at next, has a similar shape and history, but unlike M86, it appears more outlandishly original. Located 227 million light-years away from the Sun, it is a massive structure, estimated to be as heavy as 5 to 14 billion solar masses. As for its stars, most of them are young, massive, and bright blue giants, giving the galaxy a distinct ultraviolet glow. ESO 137-001 in its turn is part of Abell 3627, also known as the Norma cluster. This is a large and massive galaxy cluster located near the center of the Great Attractor. The galaxy is falling into the cluster's center at an incredible speed of almost 2,000 kilometers per second. At this velocity, the interaction with the environment becomes extreme. The galaxy collides with the superheated interstellar gas pressure inside the cluster. As a result, its own gas is physically blown out of the galactic disk, leaving behind tails that stretch for up to 260,000 light-years. These tails are magnificent and tragic. Incidentally, the mass of interstellar gas in those trailing areas is 2 to 4 times that of the gas remaining inside the galaxy itself. The galaxy is bleeding out its lifeblood. However, in this wreckage, life finds a way. It is hardly surprising that starbursts, periods of intense star formation, are a common thing here. That is, stars do not stop forming even as the gas is stripped. They ignite within these enormous streams made up mostly of hydrogen. When seen from the side, ESO 137-001 appears like a giant jellyfish floating through the endless expanses of space, with the main galaxy forming the head and the streams of young stars forming the stinging tentacles. Unfortunately, this beauty marks a dying process. As the galaxy is continuously stripped of its interstellar gas, its life expectancy diminishes too. Gas is the fuel for new stars. With not much material left in the main disk, no new stars can form here, which will greatly affect the structure of the spiral arms and the central bulge of the galaxy, eventually turning it into a dead, red fossil. On the bright side, this death spiral provides a unique laboratory for us. Scientists have a chance of finding out more about dark matter and its interaction with other space objects. By observing the behavior of the gas streams left in the galaxy's wake and seeing how the visible matter separates from the invisible gravitational glue of dark matter, we can test our fundamental theories of the universe. Speaking about the formation of newer stars, we move from a dying galaxy to one that is living fast and furious. There is a galaxy with a name that speaks for itself, the Baby Boom Galaxy. This remote object is a star-making factory without equal. Around 4,000 stars are born here every year. To understand the magnitude of this number, we must compare it to our own home. In the Milky Way, only about 1 to 2 new stars are born annually. This means the baby boom galaxy produces stars at a rate which is about 400 times more than in the Milky Way. Straightforward calculations show that on average, a new star lights up in this area of space every 2 hours. While you watch a movie, a new sun is born there. The baby boom galaxy lies around 12.2 billion light-years away from the Earth. Due to the finite speed of light, this means that what we see when observing it is not the galaxy as it is today, but what was happening just 1.5 billion years after the hypothetical Big Bang. It was a time when the universe was still in the turbulent process of forming its structure. What is taking place in the baby boom galaxy now is drastically different from what we expect to observe there in theory. According to the standard hierarchical model of galaxy formation, galaxies in the early universe should be small and grow slowly by merging. A monster of this size and activity shouldn't exist yet. Based on what we know about star formation, the reasons why stars are produced here at such an astounding rate are not known yet. It challenges our models, but it is beyond any doubt that baby boom is able to provide us with a lot of information about the early, extreme stages of our universe's evolution. Bringing our gaze closer to home, we find one of the most iconic shapes in the night sky. One of the few galaxies one can observe through a modest amateur telescope is the so-called Sombrero Galaxy, carrying the official designation M104. It lies relatively close, 30 million light-years away from the Sunday. It is a compact galaxy. Its diameter is roughly 4 times smaller than that of the Milky Way, yet it shines with an intensity that makes it easily visible. The Sombrero Galaxy's outstanding feature, which gives it its name, is a massive, dark ring of dust and cold hydrogen enveloping it. This ring cuts across the bright central bulge, creating the appearance of a brimmed hat. Observations show that it is here, within this dusty lane, that most young stars are born, shielded from view by the thick material. In addition to the peculiar ring, the Sombrero Galaxy is also remarkable for its elaborate inner makeup. It seems to be a hybrid, a chimera of 2 different types of galaxies. Observations with the Spitzer Space Telescope, which sees in infrared, show that most stars in the massive central bulge of this galaxy form a structure typical of elliptical galaxies. The stars here are mostly rather old, yellow, and red dwarfs, swarming in a spherical shape. The other stars here, on the other hand, form distinct spiral structures concealed within that elliptical cloud. How can one galaxy be both? It is thought that this phenomenon is a result of a major cosmic accident. 2 galaxies collision. Billions of years ago, a large elliptical galaxy likely swallowed a flat spiral galaxy. In this chaotic dance, their stars subsequently and inevitably mingled together. It is incredible that the galactic structures survived a merge of that scale with minimal damage. The distinctive flat disk of the spiral galaxy somehow maintained its integrity. They are none the worse for this tremendous collision and can still be observed as a unified, beautiful whole today. However, the center of the Sombrero hides a monster. Another peculiar feature in the Sombrero Galaxy is exceptionally powerful X-ray radiation emanating from the center. X-rays of this intensity usually signify extreme heat and friction. It is assumed that the accretion disk of a supermassive black hole may be its source. By measuring the speed of the stars orbiting the core, the mass of the hole is estimated to be over 1 billion solar masses. This is staggering. For a galaxy of its size, this black hole is unusually heavy. making this enormous object one of the most massive black holes known to science today relative to its host. But the mysteries do not end with the black hole. Deep surveys have revealed yet another puzzle. There are also several sources of tremendously high frequency or terahertz radiation detected within the galaxy. This type of radiation is rare and difficult to produce naturally in such quantities. Although today their nature is still a mystery, scientists continue to listen, hoping the Sombrero Galaxy will eventually whisper its secrets. Our galactic parade today is concluded with yet another object, boasting an elaborate, almost deceptive inner structure. This is the eerie M64 galaxy, rather aptly dubbed the Black Eye Galaxy. Even through a modest telescope, the reason for this nickname becomes immediately apparent. It comes from a spectacular, dark band of cosmic dust that sweeps across the bright central region, partly concealing the galaxy's center from the observer on the Earth. It looks like a heavy eyelid or a bruise in the deep sky. Due to this thick screen of cosmic dust, as well as the glare from the exceptionally bright, active nucleus behind it, it is impossible for astronomers to estimate the Black Eye's number of stars, even roughly. What we do know is that compared to giants like Andromeda, it is comparatively small and not so remote. Its radius measures 25,000 light years, and it lies approximately 17 million light years away from the Milky Way. However, the true secret of M64 is not its size, but its motion. Detailed spectroscopic analysis reveals that the Black Eye Galaxy is made up of two well-defined parts that do not agree with each other. Interestingly, the inner disk, containing the central bulge and the dense stars, rotates in the standard direction. However, the gas in the outer ring, extending roughly 40,000 light years out, rotates in the direction opposite to that of the inner disk. The most likely explanation for such a bizarre makeup is that the galaxy is the survivor of a violent history. It likely formed after two smaller galaxies collided and merged in the distant past. One galaxy was swallowed by the other, but its angular momentum was preserved, causing the outer debris to spin the wrong way. Admittedly, it would take a combination of a number of mutually independent factors for such a fascinating structure to form and stabilize. The odds of such a symmetrical success would have been minuscule, making M64 a rare laboratory for studying galactic evolution. Leaving the dense, dusty environment of M64, we now turn our attention to the opposite extreme of cosmic geography. We enter the realm of voids. These are large-scale expanses of space that are almost, or in some cases completely, devoid of galaxies or galaxy clusters. If galaxies are the cities of the universe, voids are the vast, empty deserts between them. These enormous objects take up about 50% of the volume of the observable universe. To visualize this, we must understand the cosmic web. The universe is not a uniform scatter of stars. It looks more like soap bubbles or a sponge. The galaxies form the thin, soapy walls of the bubbles, known as filaments. The voids are the empty air pockets inside the bubbles. The average void measures approximately 40 megaparsecs, or roughly 130 million light years across. However, occasionally, the structure opens up into a true abyss. The diameter of champion voids may reach several hundred million or even a billion light years. These extra-large voids are rather predictably referred to as supervoids. The density of matter in these regions is much less than in other areas of the universe. It accounts for less than 10% of the average density in the metagalaxy. Cosmology today explains their existence by the initial diversity of matter distribution. When the universe was formed, tiny quantum fluctuations created areas of slightly higher and lower density. Over billions of years, gravity pulled matter from the low-density areas towards the high-density areas, emptying out the voids to build up the galactic walls. One of the largest voids ever discovered is the Canes-Venatici supervoid, spotted in 1988. This supervoid is the second largest void known to science today, with a diameter measuring a staggering 300 to 400 megaparsecs, or roughly 1 billion light-years across. To put this location in context, the Canes-Venatici supervoid is located 1.5 billion light-years away from our Earth. The emptiness here is profound. Interestingly, detailed surveys show that just 17 galaxy clusters are located in this area of mind-boggling dimensions. And this is extremely little for such an incredibly enormous expanse of space. Furthermore, these clusters are not spread out evenly. All the 17 clusters are gathered within a comparatively small area by space standards, namely within a measly 150 million light-years. The rest of the void is essentially barren. If any gravitational interaction between them does take place across the vast gaps, more advanced technologies are called for to detect it. The scale of this nothingness is hard to grasp. The diameter of the Canes-Venatici supervoid accounts for approximately 1% of the total diameter of the observable universe. In terms of volume, it could easily accommodate 10,000 galaxies identical to the Milky Way, yet it holds almost none. Due to the immense expansion of the universe, there is no way light from our sun will ever reach those parts, and any interaction with potential inhabitants of those parts of the universe is effectively out of the question. Let us pause to consider the dimension of time involved here. What is 1 billion light-years? It is not just a distance, it is a history book. It means light takes 1 billion years to cross it. To understand this duration, look at life on Earth. The history of multicellular life forms on our Earth counts just over 800 million years. In other words, imagine a photon of light entering one side of this supervoid. As it begins its journey across the dark abyss, Earth is inhabited only by single-celled organisms. As that photon travels through the nothingness, life on our planet evolved from colonies of protozoans to dinosaurs, and finally to the emergence of humans. All of biological history fits inside the time it takes light to cross this one hole in the universe. But what is the nature of the space itself? In order to understand what space inside a void is like, you have to think of a deep physical vacuum. It is not completely empty in the philosophical sense, but it is the closest thing nature offers. It may contain wispy interstellar gas clouds or independent star clusters, but most of the supervoid contains nothing. Of course, space expanses are for the most part vacuum. Just to give you an idea about the proportions, in a galaxy, there is roughly a cubic centimeter of dense stellar matter for every thousands of cubic kilometers of space. But even this galactic space is not completely empty. Let's start from Earth to build a scale. A mark of 100 kilometers above ground is the accepted limit of the Earth's atmosphere. At this height, the pressure is negligible, yet even several hundred kilometers up, there can be found an extremely small amount of gas molecules. These seemingly negligible molecules still manage to cause friction and slow down artificial satellites. Gas concentration is much lower the further we are from a planet. But even beyond our solar system, in the interstellar medium, there will always be at least a few molecules of hydrogen in every cubic centimeter of space. In addition to that, there will be the solar wind, radiation of distant stars, and neutrinos flooding the universe. However, the vacuum inside a supervoid is different. It is deep to such a point that there is less than half a molecule of matter for every cubic centimeter of space. It is a desolation that creates a sense of existential dread. Besides, all sources of radiation, stars and galaxies, are so remote from its center that the density of their radiation is quite negligible. The sky there would be absolutely black. Compared to relic radiation, starlight is almost non-existent. As a result, all that remains is undetectable neutrinos and the faint glow of the cosmic microwave background. As I have mentioned before, there is something else to be found inside the incredibly vast expanses of the void. Apart from deep vacuum, there are also extremely rarefied clouds of interstellar gas, the pristine reservoirs of hydrogen left over from the Big Bang. Secondly, dark matter is supposed to be found inside supervoids. Even though voids are defined by a lack of matter, the faint gravitational lensing suggests dark matter filaments might still stretch across them, but today's methods of detection are hardly adequate for studying it in such low-density environments. It should be noted that the overwhelming majority of voids detected so far are located hundreds of millions of light years away from the solar system. In essence, due to the speed of light, what we are observing now is the distant past of these formations. However, not all voids are distant. Only one void lies relatively close to the local group of galaxies and is referred to as the local void. We are actually living on the edge of it. Its diameter measures approximately 180 million light years, and the distance between the Sun and the void center is about 90 million light years. We are effectively moving away from it as the local sheet of galaxies gets pulled toward denser regions. Another famous example is the Botes void, often called the Great Nothing. This is another large formation located about 700 million light years away from the Sunday. The diameter of this void measures approximately 330 million light years. To understand the scale, this is about 0.2 to 7% of the diameter of the observable universe. The Botes void was discovered in 1981 by a group of scientists headed by Robert Kirshner, confirming the theoretical arguments in favor of the existence of supervoids. The Botes supervoid is thought to have been formed as a result of several smaller voids blending together, much like smaller soap bubbles merging into one large bubble over time. It is astonishingly empty. Just 60 galaxies have been pinpointed inside the Botes void by now. For a volume of this size, this is an anomaly. Statistical models suggest such staggering expanses could easily have accommodated about 2,000 galaxies. If the Milky Way had been in the center of the Botes void, we would have found ourselves in a darkness so profound that we wouldn't have known other galaxies existed until the invention of very powerful telescopes in the 1960 seconds. Speaking about the most mysterious void in the universe, we must look further out. It lies 3 billion light years away from the Sun, in the direction of the constellation Eridanus. It is known as the CMB cold spot, or the Eridanus supervoid. This supervoid is a champion, even by supervoid standards, with a diameter measuring 1.8 billion light years. This is a structure that challenges our understanding of the early universe. It may easily have accommodated 18,000 galaxies, similar to the Milky Way. But why is it called the cold spot? When astronomers look at the cosmic microwave background, the afterglow of the Big Bang, it is remarkably uniform in temperature. However, this specific region is an anomaly. The Eridanus supervoid's temperature is from 70 to 150 microkelvin, colder than the average CMB temperature of the rest of the universe. This temperature drop is likely due to the Sachs-Wolf effect. As photons of light from the early universe travel through this vast void, they must climb out of a gravitational depression. Because there is so little matter, the gravity is weaker, but the expansion of the universe stretches the space as the photon travels. The photon loses energy trying to cross this vast gap, reaching us cooler and redder than their surroundings, leaving a cold imprint on the map of the ancient cosmos. However, even the Sachs-Wolf effect has its limits. The sheer magnitude of the temperature drop in the Eridanus supervoid presents a problem that makes astrophysicists uncomfortable. Today's standard theory of the universe's origin, the lambda CDM model, cannot give a definitive, mathematically consistent explanation to this fact. According to our best statistical models of the early universe, a cold spot of this size and intensity is statistically impossible. The probability of it forming by random chance is less than 0.2%. This anomaly so stubbornly did not fit into the accepted theory in cosmology that, at first, the measurements were dismissed as faulty. When the data first arrived from the WMAP satellite, the scientific community remained skeptical, and the equipment was blamed for calibration errors or signal noise. It was assumed to be a mistake only after several years of scrupulous measurement, and crucially, after the Planck satellite confirmed the exact same readings with higher precision, were the data finally accepted as a physical reality. The cold spot is real, and it requires an explanation. Consequently, a great number of explanations, including rather extravagant ones, were offered concerning these strange temperature properties. One hypothesis suggests that the anomalously low cosmic microwave background in the Eridanus supervoid is a result of the influence of supermassive chunks of dark energy. In this scenario, dark energy is not uniform across the universe but pools in certain regions, accelerating the expansion locally and stretching the light to extreme degrees. However, an even more profound, albeit controversial, idea has emerged. According to another hypothesis, this area is what is left of another universe that had existed before ours, or rather, alongside it. This is derived from the theory of eternal inflation. Imagine the early universe as a pot of boiling water where bubbles form. Each bubble is a distinct universe. If two of these bubble universes were to touch or collide early in their formation, the impact would release an immense amount of energy and leave a permanent scar on the fabric of space-time. The Eridanus cold spot, in this view, is a cosmic bruise, evidence of a collision with a parallel universe, be it a void, a fluctuation of dark energy, or a message from the multiverse. There is disappointingly no definitive answer yet. We are left with a mystery that sits at the very edge of human understanding. As we step back from the edge of that great void, we realize that the diversity of space really has no limits. Our survey today has taken us from the dense, chaotic nurseries of the Orion Nebula to the lonely, frozen drift of rogue planets, and finally to the silent, cold emptiness of the supervoids. In the visible part of the universe alone, there are hundreds of billions of galaxies, ranging from tiny dwarf ones to gigantic ellipticals dominated by supermassive black holes. Each of them contains billions of stars, brown dwarfs, and other large objects, as well as countless smaller bodies like planets, asteroids, and comets. Crucially, each of them is unique in its own way. No two nebulae are sculpted exactly the same. No two planetary systems dance to the exact same rhythm. The laws of physics are constant, but the combinations they produce are infinite. This means that our journey across the boundless expanses of space is quite endless. There will always be another anomaly, another star, and another mystery waiting in the dark.